Good evening, my dear JEE warriors. Welcome all the students to this amazing class for your CBSE board preparation on the number one JEE English channel, which is your Vedantu JEE English. Of course, we are going to do the most expected question, and you all know we have been doing an amazing job right now uh, conducting the classes for be it your theory part. We had long one shots, and of course the assertion reasoning and the case studies in the morning, and yes, the model mock test with the most important questions for all of you. All of this being conducted just for our dear students, and with awesome questions. And today we're going to do the numericals and the graphs. Yes, starting with the numerical part first, and then we'll go to the graphs, complete graphs for your CBSE board preparation for your upcoming class 12th board examination. All right, I look like Ronaldo with my new beard. Ooh, too bad you can't see me kicking. Yeah, while I'm teaching, I'm kicking the ball below, but unfortunately, you do not see that. All right, cool. Nice to see all of you. Welcome. Yes, the PDF will be shared, and the previous session PDF was already shared. In case you haven't noticed that yet, yep, the case studies and assertion, please check it out. The homework question was also given. You can see the PDF link is over here as well as in the comment section. Same thing will happen for this particular session. And if you have missed the current year question, please check it out. It's gone really well. Of course, the session PDF is there in the comments as well as in the description. And I don't know if you guys noticed, tomorrow morning something great is coming up, and that's your last minute physics revision. Yep, tomorrow morning. Oh my god, it's 5 o'clock. It's going to be a tough time for me. And trust me, before this also there was another state board entrance examination. So last week also I was fully busy. This week also gone. And after this, I think one more state board examination for Karnataka is going to come up. So yep. So Shreyas sir, fully occupied, fully busy, studying more, triple, double, four times, I think, than the students. So I really hope you make it all worth by getting really amazing marks, and prepare not just what we are doing over here, also go beyond, practice on your own. That is very essential. Okay. So if you have not yet given your Guru Dakshina, please smash that like button right now. And yes, of course, subscribe to the channel because second attempt preparation is going to start. BitSat, CUET, so many exams are there. Yep. SRM, VIT, all these exams, notifications, updates, strategies, papers, mock tests, everything happening out here. Cool. So let's begin with the numerical part. Here comes the first question on your screen. Vanakkam. Yes. Vanakkam. When will you end the session? Tejas, when the session is over, then I will end the session. Okay. So a coil of N turns and the radius R carries the current something. It is unwound and rewound to make a square of the same number of turns. Okay. Keeping the current same, find the ratio of the magnetic moments of the square coil and the circular coil. Okay. So let's have a look at it. You have taken a coil, circular coil, and converted into a square. So if you take a circular coil, let's say the radius is R, then the total length of that circular coil will be 2 pi R, because there are n turns into n. 2 pi, 2 pi, 2 pi, 2 pi, like that, n number of times. Now you convert it into a square coil. Now you convert it into a square coil of side A. Then that same length of the wire will be, the perimeter will be 4 times of A. So 4A, 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 like that. Again, n number of times. It's mentioned the same turns are there. So n cancels, 2 cancels. I'm left with pi r will be equal to 2A, right? Or rather, I can say r by A is nothing but 2 divided by pi. R by A is nothing but 2 divided by pi. This is what I just got. Okay. Now, the question is not about finding the radius and side ratio. The question is about the magnetic moment. We all know that the magnetic moment is number of turns into current into area. So number of turns and current is the same. So it is just that it is directly proportional to the area. So magnetic moment of the circle upon magnetic moment of that particular square is nothing but going to be the area of the circle upon area of the square. The area of the circle is pi r square. the area of the square is nothing but side square, So this is pi capital R, I believe. So pi capital R square, and the side length is A, so A square. So as you can see over here, I have R by A, which is being squared, and we just found out the value of R by A ratio is nothing but 2 divided by pi. So therefore, this particular ratio will be pi multiplied by 4 divided by pi square. Pi cancels, so it will be just 4 by pi. So that is the magnetic moment of the circle upon magnetic moment of that particular square. Is this clear, guys? But they are square coil and circular coil, so therefore magnetic moment of the square divided by magnetic moment of the circle will be pi divided by 4. Let me see how many of you gave the correct answer. Yes, you had to give the answer in terms of pi, and of course square first and then the circle, because they have asked it exactly that way. First the square and then the circle. They have asked the ratio for that. Is this absolutely clear, my dear students? This is absolutely clear. Shall we go ahead to the next part of the question or next question? Very good. Awesome. Cool. So just NIA formula, but area can be found only if you know the side length or the radius. To find the side length, the perimeter has to be the same. So each circumference into turns will be the perimeter multiplied by n number of turns. That's the logic for this. Okay, next question. The magnetic susceptibility of iron is 5500. Find the permeability of that iron at that particular saturation. Okay. So is chumma play of words, unnecessary drama out there? It's just that you have to think logically. Is there any formula relating all these terms? The magnetic susceptibility, that means basically X value is given to you as 5500. They have asked you permeability, that means just permeability of that iron is just asked. And I think there is a formula for this. Yes, the relative permeability is nothing but 1 plus susceptibility. It is 1 plus susceptibility, not 1 plus relative permeability. So it is 1 plus 5500, which is going to be 5501 is our relative permeability. Is nothing but our relative permeability. Now relative permeability, of course, we know is nothing but permeability of that medium by permeability of free space. That is relative, it's a ratio, and that is nothing but 5501. So this is what the formula is for relative. So therefore, the permeability of that soft iron will be mu naught, whose value is 4 pi into 10 to the power negative 7, the whole thing into 5501. If you want, put the value of 4, which is, pi, which is 3.14, and this multiplied by 10 to the power negative 7 multiplied by 5501, you will get the permeability of that particular thing. Yeah. If you are wondering what the unit will be, it will be Tesla meter by ampere square, if I'm not wrong. Tesla meter by just ampere, sorry. Tesla meter by ampere. Yes. So it is nothing but Tesla into meter divided by ampere. So that is the final unit. Just check it out. How much is this going to be? No, these are not necessarily PYQs. Just see if you are getting it at 6.9 into 10 to the power negative 3. Just see if you are getting 6.9 into 10 to the power minus 3 Tesla meter per ampere. That's the unit of permeability. Of course, whenever you give answers, you have to give it with units, with values, of course. Yeah. Ishant, it won't be for much long. It will be probably for 2 hours or something. Yeah, not more. Yeah. So tomorrow, Kishore will be doing formula revision. But if you want to check out my old formula sheets, I have done that over here. You can just search on the channel. Just search for class 12 formula. You will get it. Class 12 formula. You will get it. Okay. All the formula revisions, everything is there over here. Okay. So you can just check it out. Okay. Moving on to the next question on your screen, my dear students. Here it is. It says the energy stored in C4, this is that capacitor, is 27 joules. Find the total energy of that entire system. I think it's going to take quite a few steps. So let me create a duplicate. So they have asked what is the total energy given only the energy in this part. I think it involves the process of finding the charges or the voltages across all the capacitors. You have to find the energies in all the capacitors, you will get the answer. But the worrisome part is the capacitors are not of the same value. So you cannot say the charges are same or energies are same. So you have to go do individually. One thing is there, C2, C3, C4 are in parallel. So what happens is the moment I notice C2, the moment I notice C2, comma C3 and C4 are in parallel, that means the voltage drop is same for all. The voltage drop is same for all. So I can find the voltages, from that I can find the energies. So to find that voltage, I can use this particular capacitor, which is already given. So the energy in capacitor 4 is given by half C4 into that voltage square. Okay, so that energy is 27 is equal to half multiplied by the capacitance, which is 6 micro, multiplied by V square. Is that right? So V square will be, check this out, 2 goes with 6 3 times, correct? 27, 27 by 3, which is basically 9, divided by micro, that is your V square, and micro is nothing but 10 to the power negative 6. So V square is that, so V will be root of that, which will be 3 divided by 10 to the power minus 3. So the voltage will be 3 multiplied by 10 to the power 3 volts. Just check that out if you are getting it. Voltage is 3 into 10 to the power 3. Yeah, this is the third question, I think so. Yep, we just started with it. Yep. Everyone? Okay. Now that we got the voltage, so I'll just mention that, which is, that particular voltage is nothing but 3 multiplied by 10 to the power 3 volts. 3 multiplied by 10 to the power 3 volts. This is needed for solving the question ahead. So how I'll solve it? Observe now. I'm just taking another slide. So the same voltage is there for everything else, like C3 and C2 also. So energy into will be half C2 into V square. Capacitance is 2 micro. So 2 into 10 to the power minus 6. Sorry, 2 into 10 to the power minus 6. Voltage square, which is 3 multiplied by 10 to the power 3, right? Whole square. That voltage we just found out over here, which I have written down for your clarity. This is the U2 value. So you will get some value of U2. Similarly, U3 will be half third capacitance into that same voltage square. So capacitance is 3 micro. So 3 10 to the power minus 6 into voltage, which is 3 into 10 to the power 3 whole square. Okay, so I'm just going to get the value of U3 now. Okay, I'm going to get the value of U3 now. Can you guys tell me how much is U3 and U2? Yes, can you guys tell me how much is U3 and U2? Yep, quickly, think and tell me. So this 2 will cancel. So I think this is just going to be just 9 joules. Just check this out. U2 is 9 joules. Very good. Excellent. Manshi, Gokul, Nityashri. Very good. Awesome. Yeah. Mind Soul Music, like I said, around 1.5 to 2 hours the session will be. It is not going to be very long, because these are just numericals, and graphs are not plenty, but you should know it. Okay, U3. So just see this. Yeah, 3 square 9, 9 into 3, 27, 27 by 2. That's what you are going to get, which is 13.5. Yeah, 13.5. Just check this out. 13.5 joules. Okay. So this done. Only this is remaining. So how do I do that? Okay, these three are in parallel, right? So we can find the total charge in them. So we can find charge in each one of them and then add them to get the total charge. That is what one thing which we can do. Yes, correct. That is one thing which we can do. Or you can just add these three energies, from that also you can find the total charge. That is also an option. But anyways, so the total charge, the total charge, the total charge on 2, 3, 4 will be charge on 2 plus charge on 3 plus charge on 4, which will also be the charge on 1, because they will be in series. We'll find that out later on. That's okay. Q2 will be C2 into V. This will be C3 into V. This will be C4 into V. Okay, so basically Q is CV formula. That's what I have done. So the total capacitance will be nothing but C2 plus C3 plus C4, which is 2 plus 3 plus 6. This is all in micro. So minus 6. Voltage was 3 into 10 to the power 3, of course. So this is 2 plus 3, 5. 5 plus 6, guys, that's 11. 11 into 3, I believe. Yes. So that will be 33 into 10 to the power minus 3 coulomb. Just check this out. 33 into 10 to the power minus 3 coulomb. Is this what you are getting? Is this what you are getting? How many of you got it? 33 into 10 to... Yep. Awesome. Awesome. PDF, you will get it later on. Awesome. Now, whatever this charge is there is the same on capacitor 1, which is in series with the parallel combination. With the parallel combination. All these three parallel combination that is in series with this guy. In series, the charges are the same. Therefore, the value of the charge labeled 1 will be also 33 into 10 to the power, what is it? Minus 3 coulomb. Now, once I get that, I can find the energy stored in that. So the energy stored in the first capacitor will be half Q square divided by C, which is half. The value of the charge was 33 10 to the power negative 3. So 33 10 to the power negative 3. Okay, square it divided by the capacitance, which is just 1 micro. So 10 to the power minus 6. So this is going to be 33 multiplied by 33 multiplied by 10 to the power minus 6 divided by 2 multiplied by 10 to the power minus 6. So minus 6 powers of 10 will cancel. 33 into 33 divided by 2. Come on, guys. 33 into 33 divided by 2. How much is it coming out to be? 33 multiplied by 33 divided by 2. Yep. Come on. Manshi says 544. 544. Is that right? The paper can be tough, Shrey. Mentally be prepared for that. Deepak also says 544. Is that so? Everyone? 544.5 joules. But that's not our final answer. So our final answer is the total energy of the system, which will be U1 plus U2 plus U3 plus U4. So it will be 544.5 plus the other energies 9 and 13.5, 9 and then 13.5. Okay, that is also there. And the first energy, which was 27. The first energy, which was 27. Just add this up. That will give you the final energy. Yep, just add them up. People are saying 594. 594. Is that so? Just check it out. 0.5, 0.5 is 1. 10. Okay. And 13 and 27, that's 40, 50, 594. Yes, that is 594 joules. That is the potential energy of the system. So finally, when you get the answer, do not forget to block it and also always check whether the units are correct. Okay, that's it. That is our job, to check. And is it so? Yes, 594 joules. Perfect. We have got the answer. Is that okay, my dear warriors? Is that okay? Very nice question. You had a lot of things to learn from this. Voltages were same. So we found the voltage first across all of them. And the manner in which I found the voltage was using the energy formula of half CV square. So then I found the energy in the other capacitors. But to find this capacitor's energy, I need the charge. So I found the charge on these people by adding all the charges. Once I've added the charges, the total charge in series is the same. So again, series concept is used over here. And then from that charge on capacitor 1, I used half Q square by C formula and then added all the energies. That is what I got. Okay, so moving on now to the next question. The energy flux of sunlight reaching the surface of the earth is these many watts per meter square. Now this meaning of that word energy flux is nothing but how many joules is coming per second per meter square. So it's energy per unit time per unit area. That's like intensity. How many photons approximately per square meter are incident on earth? Assume that photons in the sunlight have an average wavelength of yellow color, which is 550 nanometers. 550 nanometers. Okay. So I think Aparajit, I have just done a quick recap of that particular question. I hope that was clear. Meenal, you should never ask such questions. Is this question enough? Is this session enough? Nothing is ever enough. You can never say that this session is ever enough, because no matter how much you practice, there is always a chance of doing mistakes, always a chance of doing more, always a chance of scoring more, always something that you will learn new when you practice on your own. So never just stop where the teacher stopped. You have to, it's just a torchlight which is passed to you. You have to carry the torch ahead. You cannot say, oh, teacher told me this much only, I did this much, I did not do anything at home. No, never do that. Okay. So how do we do this particular question? Well, the logic for this particular question comes like this. See, observe. The energy flux. Okay. So the energy flux which is being calculated is nothing but how much total energy which is in total is falling per unit time, per unit area. That is what you can make out from the unit as well. What is joules per second? Joules per second, and per meter square, that means per unit area. Now this total energy is a combination of all the energies of all the photons which is falling onto that plate. So imagine this, or not the plate, just that 1 meter square area. So per meter square per area, okay, on an average, okay, this is what it is. So this is that particular area which we have considered as 1 meter square, and light is falling onto it. Light is falling onto it like this. So how much number of photons are falling per unit time? That's what the question is. So the area is known. Okay, so the total energy is the sum of all the energies of all the photons. So it is the number of photons, of course, number of photons multiplied by the energy of each photon. The whole thing divided by the time multiplied by the area. Now, this is something which we need to find out. So why not take these people on the other side? So the number of photons, the number of photons per unit time. So you will have energy flux, energy flux. The area will go on the top, the area will go on the top. So multiplied by area, the whole thing will be divided by energy of that particular photon. And the energy of a photon, remember, is hc by lambda. Energy of a photon is hc by lambda. So therefore, when you calculate this value, energy flux is 1.388 multiplied by 10 to the power 3, whole thing multiplied by area, which is 1, the whole thing divided by hc by lambda. H is 6.6, 10 to the power minus 34. Speed of light is 3 into 10 to the power 8. Lambda goes on the top, which is 550. So 550 nano, which is 10 to the power minus 9. Yep, this is what it is. Yeah. Huh. Awesome, awesome, awesome. Very good. Hey, Ayappa, why man? Why spamming? What are those things? Yeah, concentrate on the class. Yeah. All right. Will they ask working of a galvanometer? They could ask. Why not? Because it's a very important construction, very important thing. They can definitely ask it. So just check it out. How much approximately is it coming out to be? How much approximately is it coming out to be? Yeah, multiply all these numbers. You have 1.388, you have 55, you have 3, you have 6.6. Just multiply 1.38 multiplied by 55 divided by 6.6 multiplied by 3. Here all the powers of 10 will come. Always take the powers of 10 separately so that the calculations are easy. 10 to the power minus 34, 10 to the power 8, of course. So see how much value are you getting eventually. Yes, 3.44, 3.45 approximately. Just see if that's the case. 3.84 is what they have got approximately. Just check it out. 3.84 or 3.44. Okay, I will just use my calculator to figure it out. 1.38 multiplied by 55 divided by 6.6. 3.83. Yeah, 3.83, not 3.45. Yeah, just check this out. It is coming out 3.83 approximately into basically the power of 10 that you should get is around 10 to the power 21. Just check it out, into 10 to the power 21. 10 to the power 21. Yep. So these many photons are falling per unit time. Photons per second. These many number of photons are falling per unit time. That is what the question was. Is that okay? Yep. Awesome. What would be the weightage of derivations? It will be usually very, very less. It is not too much. So that's why, I have told you already. I have already conducted derivations on our channel. Okay, you can just check it out. Okay, you can just search for derivations NCRT or whatever, or you will get it. You will get it. Yeah, handwritten derivations, current, electricity, electrostatic Gauss law, everything is there. Okay, if you just type it over here, you will get it. Derivation physics. Okay, just search for derivation physics. You will definitely get most important derivations. CBSE board, last year I had done this. This is a big 6-hour class. Most important derivations for CBSE board by me only. Okay, it is 6-hour long class. If you want, you can definitely check it out. All the derivations are there, handwritten format. Okay, yeah. What is watt per meter square? That is basically the unit of the energy flux, which is, like I said, energy per unit time per unit area. Energy per unit time is watt, per unit area means meter square. That is why that watt per meter square. Is that okay? Okay. Yes. Awesome. Awesome. So this is also going to be per meter square also. Why? Because whatever calculations we have done is also for 1 meter square. So this calculation will also be for every meter square. Yeah. Yeah. So is it not the photons per area also? Yes, it is also per unit area because we have chosen this special value, 1 meter square. Remember the area value which we substituted over here was 1 meter square, was 1 meter square. Understood? Clear? Shall we go ahead to the next question coming up on your screen? Here it is. The photons emitted during the de-excitation process from first excited level to the ground state of hydrogen atom is used. So in the de-excitation process, what will happen? A photon will be emitted. That photon is used on a photocell. That means like a photoelectric effect, in which the stopping voltage is 5 volt. Calculate the work function of that particular cathode. Yeah, I hope this is absolutely clear. Okay. Is it better to write what we think or leave it empty? It's better to leave it empty rather than writing it wrong. Okay, because if you write it wrong, then maybe you might trigger that examiner. I mean, either ways you will lose marks. I mean, it's nothing great. Why do you want to write a wrong unit? Yeah, better not write a wrong unit. Better not write it at all. Yeah. Okay. Cool. So let's do this particular problem. Okay. Now over here, you should know the energy levels of hydrogen. You should know the energy levels of hydrogen. I think I had posted it somewhere here. Yeah. So this is the ground level where the energy is minus 13.6 electron volt. Over here it is minus 3.4. In the n is equal to 2, n is equal to 3 is minus 1.51, and so on and so forth. Just remember a few values because generally those values will come again and again. So what has happened over here is that the electron has gone from the first excited to the ground state. This one over here is the first excited state. This is basically your ground state. So when you jump from here to here, when you jump from here to here, this energy difference will go into the energy of that photon, will go into the energy of that particular photon. So therefore, I can say that the energy of that photon is energy at level 2 minus energy at level 1, E2 minus E1. What is that energy at 2? You should know that value. It is minus 3.4. Now, if you don't remember the values, the simple way is, remember, energy of any nth state is minus 13.6 divided by n square. So you can put n is 1, you will get minus 13.6. You put n is equal to 2, so 2 square is 4, so you will get this as minus 3.4. You put n is equal to 3, which is divisible by 9, then you will get minus 1.51, so on and so forth. That is the easy way if you do not know this particular table. So now this is E2 minus E1. E1 is nothing but minus 13.6. So basically it is 13.6 minus 3.4, which is nothing but 10.2 electron volt, which is the energy of that particular photon, which is the energy of that particular photon, my dear students. This photon, this particular photon is falling on somebody else. Yes, this photon is falling on a photocell whose stopping voltage is given. Question is, find the work function. We all know for a photoelectric effect to happen, the energy of the photon should be work function plus E into stopping voltage. So energy of the photon is 10.2 electron volt. Work function is what we have to find. Stopping voltage is 5, so this will be 5 electron volt again. So move this here. So work function will be 10.2 minus 5. Yes, did you get it? 10.2 minus 5. Exactly. So what will the answer be? It will be 5.2 electron volt. So finally block this. This is your final answer. Loved it. So two chapters or two concepts are combined here. First concept of atomic structure, atomic spectra is combined with photoelectric effect. Two concepts combined together to give a big nice question. Okay. When should we take EI minus ER? I don't think there will be a need for taking EI minus ER ever. You should always, whenever it's higher minus lower, then it is the energy difference of two things. So you will always try to make it positive. I don't know why you will make it EI minus ER or EI minus EF. I don't think there will be a need like that. Yeah. Is that okay, JEE aspirant? Just see, if you are getting a negative answer, just make it positive, man. Don't break your head so much. EF minus EI, sir, I'm getting negative answer. Immediately change it off. If something maybe at that point of time in the stress of the exam it is not clicking, why you are getting an extra sign. So always make it positive and proceed. Don't waste your time why I'm getting negative. Okay. Now this particular question, I think there is some graph which we have to draw. The EMF and the resistance are connected across a variable resistor across that, and the voltage versus current graph is drawn, and the value of external resistance when it is 4, the current is 1 ampere, and when the external resistance is 9, the current is 0.5 ampere. Find the values of EMF as well as your internal resistance. Very interesting question. Yeah. Sir, Ella ready agithinla. What do you mean by that, Arfin? What do you want me to ready? Become ready. I understand what you said, but ready in what sense? What? Somebody party is there or what? Thank you, Kevin. Hi, Nikhil. Nice to see you. Hi, Vignesh. Nice to see you. Vanakkam. So this particular thing is based on a particular graph, which you should definitely know. And we will be doing that during the revision phase also of the graphs after this numericals, where if you have voltage over here versus the current, voltage over here versus the current, this particular graph looks something like this. Yes, this graph looks something like this. Yep. And the equation is given by, at any particular thing, at any particular value of current, this particular voltage V is given by E minus I into R. This is that equation. It is a straight line equation with negative slope. It is a straight line equation with negative slope. V is the terminal voltage, E is the EMF, I is the current, R is the internal resistance. Also, do not forget, this terminal voltage is also going to be I into R. And the reason for that is very straightforward. See, this is our external resistance. This is our battery. This is our internal resistance, something like this. This is R, this is E. There will be obviously some current which will be going into it this way. So this is how the current will be flowing. So that voltage that we are talking about is this particular voltage, the terminal voltage across the terminals, which is also the voltage across the resistance. So that is why it is also equal to current into resistance. That is why it is also equal to current into external resistance. This is also going to be true. Okay, sir. Now let's solve the question. What is the question? The question says, when this is this, current is 1 ampere. Okay. Current I know, resistance I know. So if I use this particular equation where current into external resistance is E minus IR, this current is 1 ampere. 1 ampere multiplied by R. EMF I do not know. In fact, I have to find that out. Current is 1. Resistance external is 4. Therefore, 4 is equal to E minus R. That is equation number 1. That is your equation number 1. Similarly, what I will do for the second time, when it is 9 ohm, current is this much. When it is 9 ohm, current is this much. So current is basically 0.5. Resistance is basically 9. EMF I do not know. Current is again 0.5. Internal resistance I do not know. Okay. So this is basically 4.5 is equal to E minus, or you can just do one thing. You can just write it as 9 by 2 is equal to E minus small r by 2. If we want, just multiply by 2. So 9 is equal to 2E minus R. 9 is equal to 2E minus R. That is equation labeled 2. Everybody fine till this point? Yeah, these equations we got. Now what do we do next? You have to solve these two equations, right? So let's solve it over here. So what is the best way to solve it, guys? I feel we should just subtract these two. I think then RR will get cancelled. So 9 minus 4 will be 2E minus E. This R and R will get cancelled. Is that right? We have just subtracted the two equations. So 5 is equal to E, or EMF is basically 5 volts. Okay, so that is one of the answer. Perfect. So use it over here. So if you use it directly over here, what will you get? 4 is equal to 5 minus R. So therefore, small r is equal to 5 minus 4. Therefore, R is equal to 1 ohm. So that is your second answer. So 5 volts and 1 ohm. Great. You will get full marks for it. Understood? You have to show all these working steps, guys. So I'm solving it for you only for one reason. Why? Because I want to show you the working steps. If you don't show the working steps, they will cut marks. Here also, actually, you should show that do equation number 2 minus equation number 1. So subtracting the equations, subtracting the equations, this is what you will get. So write all these steps. All right. Very good. Awesome. Okay. Manshi, I think it's a little too late for improving the handwriting, but I'll tell you what you can do. Okay. So usually I suggest, see, for example, this is your answer sheet, right? So if your handwriting is not good, oops. So these are your paper lines. So that your paper is presentable. Okay. So that your paper is presentable. What and all things you can do means, one thing, draw mentally or either via light pencil a margin. Okay, what you should do with a light pencil, just think about a margin over here and margin over here. Don't make the margin too big. It should be very close to the edge of the paper. Don't write till the edge. That is one thing. So this is basically your margin. What is this? This is basically your margin. Please erase it off. Erase this later. Erase this later. Number one thing. Also, try to keep the number of words restricted and write big. Don't write very, very small like this, and don't once hold the paper like this, then you're holding the paper like this, then you're holding the paper like this. Don't do that. All this is not allowed. Basically, don't write very, very small. So please don't write very, very small. Then also don't hold the paper like this, then like this, then like this. So this is also wrong. Hold the paper in one direction which you are comfortable with. Don't keep changing the positions. Okay. What is the best thing that you can do? Write medium size. Don't write very big also. Write medium size. So this is how, this happens. So this is much, much better. And in this particular space, generally keep around 6 to 9 words. 6 to 9 words. That is recommended. That is what is recommended. Okay. Also, whatever points you write, keep it on different lines. So whatever, for example, you're writing the answer, always start with, so whatever the question's statement, whatever is because, and then leave little space, number 1 point, number 2 point, number 3 point, like that. Okay, don't write it one after the other. And then finally, hence conclude, do this. Always whenever you draw diagrams, try to draw it either on the right side or left side. Keep consistency. So if you have a diagram, please draw that particular diagram properly, between those lines. Okay, so draw your diagram, and if there is a formula, so whatever that formula is there, please block it. Whatever that formula is there, please block it. This is how your paper will look very, very neat, presentable. Another thing which you should do, is, say for example, you wrote something. Say for example, you have written something. So the value is not possible, and then you realize, no, the answer is possible. Then do not do this. Do not do this. This is not correct, guys. This is definitely not the right way to do it. So erasing it like this, not allowed. Rather, just do this. Just do this. So if you want to cancel something, just put a line that looks very, very neat. Is that okay? Yeah. Yeah. I hope this is absolutely clear. Yeah. So this is how things will be very, very neat and tidy. And be slow. So whenever you are writing, don't be very slow also. Just be steady and slow, I would say. So your speed should be steady and not very, very fast. Steady and decently paced. And decent pace should be there. Yeah, so that suddenly it is fast, suddenly it is slow. And take breaks in between. When you take breaks in between, then what happens is your hand gets rest and your handwriting is good. Like for example, you have finished one big question, your hand is spinning, read through the question, think mentally what you should do. Okay, what is that? Take rest. Meanwhile, keep moving your fingers and then start writing so that your hands don't sweat or they are not under strain. Clear, everyone? Okay. No, don't use Tukka strategy in board exams. Actually, you should avoid it as far as possible. It is Chumma for ultra legend people only. Okay. Here is the question coming up on your screen. If the side AC of the above prism is now surrounded by a liquid, this is your prism. It is surrounded by a liquid on one side, as you can see. Determine the light ray if it continues to graze along the surface or undergoes total internal reflection, or does it come out over here? Okay, does it refract? What happens? We do not know. We have to find it out. Draw the ray diagram followed by the incident ray with the corresponding angle values. Okay, I think I don't have a separate diagram for this. Okay, so I'll just draw it here again. There is no other way I can do it. So this is what it is. Okay, this is our prism. This is our prism whose refractive index, is it given to us somehow? Square root 3. Prism's refractive index is not given only. Is it 1.5? draw the ray diagram, or maybe in the solution somewhere they have given. Uh, they have, okay, whatever, they have not given for some reason, I don't know. Okay, let's just ignore it for now. Determine the ray continues to graze, draw the ray diagram. Okay, the liquid's refractive index is given by 2 by root 3. So the liquid which is there over here, that liquid which is there over here, that liquid's refractive index, they have given it as 2 by root 3. That they have given it as 2 by root 3. Is that right, everyone? Yeah. Graze along the surface or not, that is what we have to figure out, my dear students. Okay, nothing as such is known to us. Nothing as such is known to us right now. Okay, so is the refractive index of the prism given? Mm, wait. Yes, so basically there was one missing piece of information which is not there in the question. So I'll tell you what that missing piece is. Now I just saw the solution and then I realized that it is not printed over here, because you can see the statement itself starts with if the side AC of the above prism is now. So there was something about this. So what was there above? I'll tell you. Without the liquid, without the liquid, without the liquid, the light ray just got internally reflected, just got internally reflected in the prism. This is given to you, and then the other statements are there. So this particular piece of information was missing, so I'm just adding it. No, root 2 is not given to us directly. It is just given that the light ray just got internally reflected when there was no liquid on the other side. So the logic for that then goes as follows. So just imagine when the liquid was not there and the light ray will come from the other side like this. As soon as it falls, as soon as it falls over here, it is falling perpendicular. It is falling perpendicular over here. So I think it should just continue in that same path. So it will just continue like this over here. It will just continue like this over here. Yes, the angle of refraction will be the angle of incidence. It is normal incidence. So this is basically normal incidence. So there is no bending only of light. Light is not bending. So now if you just probably draw a perpendicular over here, and since this angle is 45 degree, since this angle is particularly given as 45 degree, we can see if this is 45 degree, if this is 45 degree, obviously even this particular angle will also be 45 degree. This angle will also be 45 degree. Okay, this angle will also be 45 degree. Everything will be 45, 45, 45 degree. All angles will be congruent. Even this angle will be 45 degree. Everything is 45 degree. Since it is just getting internally reflected, it is given just getting internally reflected. So this 45 degree must be the critical incidence, must be the critical incidence. So therefore, sine of critical incidence is 1 by refractive index of that prism. So sine of 45 degrees is 1 by refractive index of the prism. So 1 by root 2 is 1 by refractive index of the prism. So refractive index of the prism is root. So that's how I get the refractive index of the prism. Yeah. Is that absolutely clear? Yep. Is this absolutely clear? Awesome. Now use this for the next part. So the refractive index of the prism is basically root 2. Is basically root 2. Now let's see what happens when the light enters. The light will still enter normal incidence and it will continue to go like this. So there is no change as such. So this is still going to be 90 degree. Of course, this is also going to be 90 degree. So this is still going to be normal incidence now with the fluid. This is with the fluid, of course. And now if you drop a perpendicular over here, you will notice this is still 45 degrees, but it may not internally reflect, it will refract. What happens, we do not know, because outside medium has changed. Outside medium has changed. So for that, we will find what is the relative refractive index. What is the relative refractive index of the dense medium, which is our prism, with respect to prism, which is supposedly dense, with respect to the liquid, which is considered optically rarer. So that relative refractive index will be refractive index of the prism by refractive index of the liquid, which is root 2 divided by 2 by root 3. So root 3 will go on the top, root 2 will be here. So that is same as root 3 by 2. Root 3 by 2. So that is the relative refractive index of the prism with respect to the liquid outside. With respect to the liquid outside. From this, we can now find what could be the critical angle for that refraction. So for that new critical angle which will be there, so sine of that new critical angle which will be there will be 1 by this new relative refractive index, which is 1 by root 3 by 2, which is root 2 by 3. So that is sine of that critical angle. But in the question, they have given root 2 by root 3 sine is 54.6 degrees, right? So basically this is telling me this is nothing but, just see over here, it is given to me. Yeah, sine of 54.6 is root 2 by root 3. So hence, this critical angle is nothing but 54.6 degrees. But the angle of incidence is 45 degree. This is definitely telling me 45 degree is less, which is the angle of incidence, is definitely less than 54.6 degree, which is your critical angle. So what happens when your incident angle is less? Will it internally be reflected, or will it graze, or will it refract? No, total internal reflection will not occur. Yes. So what will happen? Yes, there will be no total internal reflection. It will definitely refract. What will it do? It will definitely refract. Definitely. Yeah, when it is more than the critical angle, that's when it gets internally refracted. Okay, perfect. So let's find out what happens then later on. This part we have already found. So now I can say sine of incident angle upon sine of r, is nothing but, you can say the light is going from the glass to the thing. You can just write it like this. Otherwise, refractive index of the prism into sine of incident angle will be refractive index of the liquid into sine of angle of refraction. This is not IC, this is just I. This is sine of I. We don't even need this actually. We don't even need this. That's it. So now we can solve this, guys. Now it is not at all difficult. Yep. What will this be? Come on. Mu p. What is it? It is nothing but root 2 sine of incident angle, that is sine of 45 degrees, is equal to refractive index of the liquid 2 by root 3 sine of r. So this will be root 2 multiplied by 1 by root 2. So this will be 2 by root 3. This will be just sine of r. I'm just using Snell's law over here. N1 sine I1 is equal to N2 sine I2. That's it, Snell's law. That's all. Is that right, everyone? Okay. So root 2 cancels. Sine of r will be root 3 by 2. This is a standard thing. R will be how much? 60 degree. Which means after this, the light ray will go like that, and this particular angle will be 60 degrees. And I think in the question we had to also show the path, also draw the ray diagram, and also find out what happens. So we have proved that the light will not internally reflect, it will refract. That's one thing, you have to highlight it. And second thing, it will refract at 60 degree, and show this diagram, you will get full marks. Is that okay? Very good. Excellent day. Awesome, guys. Many of you got it now. Great, 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 great. Very good. Yeah. Now, moving on to the next question. Yeah, this was the same thing. See, 60 degrees they have got. They have also got the same thing. Over here, there is a beam of light consisting of two wavelengths, that is a bichromatic source, which is used in Young's double slit experiment. When you use two colors at the same time in YDSE, you will get two fringe patterns of different fringe widths. At the center, both the fringes bright maximas will coincide. You will get a bright maxima of both the things. But eventually, since the fringe widths are different, they will not overlap perfectly. But after certain fringes, again overlapping will occur. Again, they will not overlap properly. Again, after the LCM, they will overlap. So there will be some random pattern, but again that pattern gets repeated again and again after their least common multiple. Is that clear, everyone? Okay. AK Shara, please don't spam. Please concentrate on the class. Find the distance of the third fringe on the screen from the central maxima. What is the least distance of the central maxima where both the things will coincide? Both the things will coincide. For time management, please check out my strategy video, which I have already made on the channel. Okay, just go to the live section. Okay, time management, I have given what you should do right over here. Yeah, this one. CBSE tough paper strategy, last minute plan. Please check it out. It's there in this particular video. So the first part, what we are doing now, third bright fringe. Okay, so y n for bright is n times lambda capital D by small d. Because it is third bright, n is 3, lambda is 650 nanometer, so 10 to the power minus 9. Capital D is not given at all, so just leave the answer in capital D and small d. Yes, is that right? There is no value of capital D and small d given. Just check it out. It is not at all given. Yeah, it is not given. So 650 into 3, 600 into 3 is 1800, 50 into 3, 150. So 1950 into 10 to the power minus 9, capital D by small d. It is not given. So leave the answers in that format. So this is the distance from the central maxima. Central maxima. Whose distance? Third bright fringe distance. Okay, so that was the first part. Now let's go to the second part of the same question, which talks about where will both the maximas meet? Where will both the maximas meet? Okay, think about it. How do we do this? Okay, great. What is the meaning of capital D and small d? It is this, no? Young's double slit experiment, forgot? So you have two slits over here. This is your source. This is the distance between the slits, and this is your screen. The distance between the slits and the screen is capital D, and this is where you get the central maxima. Central maxima. The third maxima will be here. First maxima, second maxima, third maxima. So third maxima will be over here. Is that fine now? Yeah, that is the rough diagram, just so that you know. Central maxima is directly in front of the midpoint of the slits. Yeah, directly in front of it. Okay. So now the question is, where will they meet? If they are meeting, if they have to coincide, one thing is for sure, if they have to coincide, y of the first wavelength should be y of the second wavelength. I do not know whose maxima will coincide with whose maxima. Okay, so I will just write it as n into lambda 1 capital D by small d is equal to m I do not know, some natural number, lambda 2 d by small d. What is n and m? Some nth maxima coincides with mth maxima. Nth maxima of wavelength 1 coincides with mth maxima of wavelength 2. D will cancel. D will cancel. Exactly. Yeah. Very good. So D will cancel. So I am just going to get n by m is equal to lambda 2 by lambda 1. Okay. So what is lambda 2 and what is lambda 1? Check it out. 520, 650. 520 is lambda 2, second wavelength, 520 nanometer. And the first wavelength is 650, everything in the same units. So therefore, n by m would be, yes, so this is divisible by 13, 0 nano cancels, so 13. So this will be nothing but 4 divided by 5. What does this mean? Is that means the fourth maxima of first wavelength, which is 650 nanometers, coincides with whom? With fifth maxima of whom? The other wavelength, which is 520 nanometers for the first time. For the first time. It's not like they will not coincide again. They will coincide, but again that coincidence will happen at 8 and 10. Just multiply by 2. Then multiply by 3, it will be 12 and 15. So 12th maxima will coincide with 15th maxima. So that coincidences will keep on occurring later on. But this is the first time this coincidence will occur. Is this part clear, everyone? Everyone? Awesome. 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 Everyone? Great, 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 great. Awesome. Now, 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 what is next? What is next? That is not just the question. The question is, what is the distance they have asked? So either you find this or you basically find this. Either one of them will give you the answer. Let's say you find the fourth maxima. So that distance which you have to find, that least distance, will be y4, or you can also find y5 for this wavelength, but I'm just going to stick with y4 now, which is 4 times lambda 1 d by small d. So lambda, what is lambda over here? What is lambda? 650 capital D by small d. What is it going to be, my dear students? Come on. What is it going to be? 2600? 650? Yeah. So what is it going to be, guys? Yes. 2600 capital D by small d is that distance. Don't confuse with that small d. So that particular distance will be 2600 capital D by small d. Very nice. Very nice. But remember, all these answers were in nanometer. So this, do not forget, put 10 to the power minus 9. Also put 10 to the power minus 9 over here, just for that nano part. Just because of that nano part. That is it. That is the answer. Yeah. Great. Awesome. Awesome. Very nice. Okay. All right. Next question. Calculate the capacitance. Power factor is unity. Quality factor in the circuit. Now you might say, sir, quality factor there, not there, not there. So this can also come as a passage. That means a case study. They can tell you the quality, the sharpness of a LCR circuit is measured by Q, where the formula is 1 by R root L by C. So if this comes as a passage, then what will you do? You cannot then blame, sir, Q factor is there, not there, out of syllabus. No, then you cannot argue. If they give you in the passage that formula, that's it. It is there. You cannot say it is out of syllabus. Is that okay? The value of capital D by small d is not given. You leave the answer in capital D and small d. Yes, we'll be discussing important uh, graphs. No, because some students suddenly say, sir, that is there, that is not there. So that is why I'm telling. because sometimes students think, oh, should I study if a passage does not have this particular question? You have to do it. Okay. Power factor is unity. So let me just create a duplicate over here. Okay. So power factor is unity means one thing for sure. It is resonating. Resonance is occurring. And if resonance is occurring, if I know L and if I know omega, that's it, my job is done. So omega is 1 over root LC. So omega square is 1 by LC, correct? And we have to find what? The capacitance. So therefore capacitance is 1 by omega square L. So therefore capacitance will be 1 by omega square. Omega is 100. 100 square multiplied by inductance, which is 200 milli, which is 10 to the power minus 3. That is what it is. So therefore the capacitance will be, check this out. I think I'm getting 1 by 2 over here and some powers are there. Okay, so 100 square is 10 to the power 4. This will make it 10 to the power 6. Minus 3 will make it 10 to the power 3 again. So by 10 to the power 3, this is 0.5 into 10 to the power minus 3 capacitance. Therefore, capacitance is 0.5 millifarad. So this is the first answer which we have got for this particular question. Is this okay? Everyone with me? Yes, 0.5 millifarad. Yes, Anirudh, of course, there will be videos which will be made for the second shift, JEE Advanced and other exams. But since board exams are going on, very few people who are from state board who do not have exams or are droppers will be studying. So, I mean, obviously we cannot leave our board students too. So that's the reason why we are focusing on boards now. But as soon as the board exams are over, immediately we are starting off with your JEE preparation for second attempt as well as for JEE Advanced, both. Because some students might be scoring high, right? Okay. Now, second part, Q factor. So how do we do this? Q factor. For that Q factor, what is the formula? It is 1 by R root of L by C. So resistance is 10 ohms. Inductance is 200 milli, which is 200 into 10 to the power minus 3. Capacitance was 0.5 into 10 to the power minus 3. Yes. What's that power factor going to be, guys? Come on. What is that power factor going to be? Yep. Check this out. Minus 3 cancels. 0.5 is, well, 0.5 is nothing but 1 by 2 goes on the top. So it will become root of 400. Root of 400 is 20. 20 by 10 is basically 2. So the power factor, sorry, power factor I'm saying, Q factor is 2. Yes, the quality factor, we have found it out. Last part is find the average power in the circuit. Okay, last part is calculate the average power in the circuit. Now the average power in the circuit, because the circuit is in running in power factor of unity, it will be V RMS. Is it given somewhere? Oh, the voltage is only not given. Yes, the voltage is not given, right? I mean, did we miss it somewhere? No. Okay. V into current into cos phi. Yeah, it is not given only anywhere. Just check it out. Yeah. So yeah, that's all. So we cannot do anything much about it. So current is nothing but the total voltage by that resistance. Cos phi was 1. So it will be V square by resistance. Resistance is 10 ohm. So if voltage was given, we can do it. But I think in the solution slide, they might have given some value of voltage. So yeah, they have taken it as 50 volts. See, they missed that value. I think in the copying. So this was apparently 50 volts AC source. So if this AC voltage source is given to be 50 volts, then we can write it down directly over here. Yeah. So then assuming this is 50 volts, then this will be 50 square by resistance, which is 10. So 2500 by 10, which is basically 250 watts. 250 watts. Is that okay? Yeah. Very good. So I'm just adding this value by looking at the solution because I think there was a printing error while copying this question. Yes. Okay, Cool. That was that answer. Moving on to the next question, guys. Get ready. Get ready. Okay. If it is given plate, take it as a conducting sheet. If it is given as a uh, what is what do you say? If it's just given as a sheet, there is a insulating sheet, or or they will say a rubber sheet. Okay, then you will take it as sigma by epsilon. Another way is on the surface of the conductor, it is sigma by epsilon because inside there is no field. But when the field goes both sides, then it is sigma by 2 epsilon. I'll tell you one easy way, guys. See, when you have a plate which is conducting in nature, either they give you plate or they say a conducting sheet, the electric field will go here also, it will go here also. But imagine you have just a, I would say, maybe something like this. Something like this. And the field is only coming out on one side. If it is coming on one side, then it is just sigma by epsilon. If it is going both sides, that number 2 will come. So it will be sigma by 2 epsilon. Two sides 2, one side 1. That is the easy way to remember. Okay. So this is basically for the surface of conductor, just outside the surface of a conductor, or for a non-conducting surface also. Non-conducting surface. Both the times you can use it. Is that okay now? Clear? Moving on to the next question. Photoelectrons are coming out of a metallic surface with UV light. Minimum amount of energy required is this much. Calculate the energy of the radiation, energy of the photoelectron. I think direct calculation based question. Yes, come on guys, direct calculation based question is there. Yep. So the first part is find the energy of the radiation. The wavelength of the light is already given to you. Now, is the answer required in joules or electron volt? I think it is in joules, so we'll stick to joules. So for the first part, energy of that incident photon is hc by lambda. H is 6.6, 10 to the power minus 34. C is 3 into 10 to the power 8. The whole thing divided by the wavelength, which is 330 into 10 to the power minus 9. Best part, 66 and 33 cancel. So if you want, you can write it as 66 by 33, which is 2, multiplied by 3, but one decimal was shifted. So 10 to the power minus 1 compensation, 10 to the power minus 34 is there, 10 to the power 8 is there, and also this 0 and minus 9 will make it 10 to the power minus 8. Is that right? This 33 cancelled with 66 became 2. This 0 merged with minus 9 became minus 8. That extra decimal I wrote it down over here because it was written as 66 now. And 3 into 2, which is basically 6. Just check this out. So 6 into, what is this power? 8 goes on the top, becomes 8 plus 8, which is 16. Yep, 8 plus 8, which is 16. 16 and minus 34. Okay, this will become 18 minus, and this will become minus 19. Minus 19, just check it out, 10 to the power minus 19. Everyone, just check it out, 10 to the power minus 19 joules. So that is your energy of that particular photon. Okay. Next, kinetic energy of the photoelectron. Minimum energy required is this much. This is basically your work function. And we know the equation goes like this. Energy of the photon is equal to work function plus the kinetic energy. Therefore, the kinetic energy will be energy of the photon, which is 6 into 10 to the power minus 19, minus the work function, which is 3.5 into 10 to the power minus 19. Do you get it? Just use the photoelectric equation. Everyone, yes, what is the answer? 6 minus 3.5. That's just going to be 2.5, 10 to the power minus 19 joules. Since everything is in joules here, leave the answer in joules, don't convert it into electron volt. It is okay. Just convert it into, just leave it as joules only. So 6 and 2.5 should be the answer. Yeah, 2.5 and 6. Perfect. Exactly. We got the answer. Awesome. Moving on to the next question on your screen. There is a bar magnet of 3 centimeters in length and has 2 points along the axis, one at 24, one at 48 centimeters. The ratio of the fields at that point will be. Since we are talking about axial points, the magnetic field on the axis is given by mu naught by 4 pi constant. On the axis, it is 2 times magnetic moment divided by x cube. The same magnet, the same constant, only x will change. So it is inversely proportional to x cube. So the magnetic field at point A and magnetic field at point B will be xb by xa, the whole cube. What is xb and what is xa? Xb is 48. This is 48. Xa is 24, the whole cube. So 48 by 24 is 2. 2 cube is basically 8. So 8 is to 1 is the answer. 8 is to 1 is the answer. How many of you got it? Let's see. Very good, the Gokul. Yeah. Awesome. Very good, Shiva Prasad. All right. Microscope based numerical. Did you see my yesterday's class? I have done a very interesting numerical. I don't know whether you saw that. Where did I do it? Yesterday only. Yeah. Check this. Towards the end, I have done it somewhere. Yeah, this is that microscope based numerical. See, compound microscope, objective lens, very important. And I have taken both the cases. One is for least distance of distinct vision also, and one for infinite distance. Both magnifications we have found. Yes, just check this numerical. Yesterday's session only. CBSE current year guess questions. Okay, just do that. All right. Cool. Cool. Sir, in the question, cos phi is 1 means cos phi is r by z. So cos phi is 1 means r is equal to z. Yes, Sid. I mean, where did that question go of our AC circuit? This one, right? So at resonance, what happens? Remember, so many things happen actually. Uh, your inductive and capacitive reactance cancel each other. XL and XC are equal. XL is equal to XC. Your resistance in the phasor diagram will be like this, which will also be the impedance. So impedance will also be R. The phase angle will be 0 degree. So cos phi will be 1, which is the power factor, which is basically your power factor. So power factor will be 1. All these things hold true. Okay? Clear? Yeah. Let's move. This particular question, my dear students, let's try it out. A rectangular loop of side 8 centimeters and 2 centimeters with a small cut is moving, okay, in the region of field. Magnetic field is 0.3 Tesla. It's also given the field is perpendicular to the plane of the loop. What is the voltage developed if the velocity is this much? And first it is going along the longer side, then it is going along the shorter side. For how long will the voltage last? Okay, so I will do both the situations on two separate figures. See, right now the loop is here. Imagine you are taking it out along the longer side. So what will happen is, imagine what will happen is, the loop will come over here. The loop will come over here. This is the moment when the magnetic field will start reducing. And as you take it out, and as you basically take it out slowly like this, you can see the flux in it will reduce until you take it out completely and you bring it over here. So everything starts over here. This is when t is equal to 0, and it ends when it is completely out. This is when it is completely out. This is when it is completely inside. So the entire loop was inside over here. Notice that. And after this, slowly the flux starts reducing because only a small portion of it is inside the flux, inside the field. And once it is completely out, that's when the electricity stops getting generated. So if you ask me how much time it will take, it's not that difficult to see that the side length is 2 centimeters, time is distance by speed. So this time is nothing but distance divided by the speed with which it goes. So it is 2 centimeter divided by the speed, which is 2 centimeters divided by 1 centimeter per second. So it is just 2 seconds. So the time taken to go out is just 1 second. Is that clear, everyone? Awesome, awesome. Same thing you can also apply for this guy, and you can visualize this too. When this guy probably reaches over here, that's when the loop is completely inside, and when it starts coming out and eventually it is completely out, so this is time is equal to t2 when it is completely out. So during this duration, the EMF will be generated because the flux is continuously changing. So to find this time, which will be again distance by your speed, of course, the distance over here is 8 centimeters. 8 centimeters, it is mentioned over here. I hope you can see that. Speed is again 1 centimeter per second. So this particular time will be 8 seconds. So we have found out the answer. How long does it last? How long does that time, how long does the induced voltage last? So both these answers we have found. How long does the induced voltage last? But now there is another part. What is the voltage developed? That is also asked. What is the voltage developed? What is the voltage developed? So for that, just see whichever length is coming out, that will be the length of the conductor which you should consider for generating the EMF. So EMF is magnetic field into length into velocity. So the length which is perpendicular to the velocity. Always choose that particular length which is perpendicular to the velocity in that magnetic field. So in this case, the length is 8 centimeters. So field is zero point 0.3 Tesla, length is 8 into 10 to the power minus 2, speed is 1 centimeter per second, so minus 2 again. So 8 threes are 24, so this will become 2.4 into 10 to the power minus 4 volts. So this can be written down as 0.24 into 10 to the power negative 3 volts, but we can write it as millivolts as 0.24 millivolts. So that is the EMF in the first case. That is the EMF in the first case. How many of you got it? Yep. Very good. Awesome. Yes. Tag. Oh my God. Thank you so much. Yeah. Where is tag? Tag, 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 tag. Thank you so much. Need to mention tag. Thank you. Tag, please make last minute NCERT revision. Thank you so much for your contribution. And let me show you, tag, what we have just done. I have heard you, and I have heard you. And look at this, exactly what you asked, last minute NCERT revision. But I have kept it in the morning because many students will watch this session as recorded also in their night, and you too will be revising. And tomorrow morning, I don't want you to leave you blank. You might be scared, you might be tense. So that's the reason why I'm coming in the morning. We'll keep it for 1.5 hour max, not more than that. Quick revision. We'll do the revision really quick. Okay, cool. So I've heard you. Great, great. And thank you so much for the amazing contribution, and means a lot when you guys show your affection and love with this small gestures. Thank you so much. Yeah. Got the answer. Very good. Similarly, do it for the other one. Similarly, do it for the other one. Second time, E2 will be BLV, magnetic field 0.3. Length this time will be this length. Yes, this length, which is 2 centimeter. So 2 into 10 to the power minus 2. And velocity is again 1 centimeter per second. So 0.3 into 2, which is 0.6 into 10 to the power minus 4 volts. If you want, you can write it as 0.06 10 to the power minus 3 volts. So this will be 0.06 millivolts. So that is the second EMF. So 0.06 versus 0.24. Those are the answers to these questions along with the times. If you write it all this like this, you'll get full marks. Very good. You got the answer, Narendra. Awesome. 0.06 Gokul. Very good. Yeah. We'll end the morning session by 6:30. We'll target 6:30. You're going to keep it very quick, fast revision. Okay. Great. A, B, B, C, C, D, D are the resistors 1, 1, 2, 2 ohm respectively connected in series between A and C is a 1 volt cell of 2 ohms, A being positive. B and D is a 2 volt cell of 1 ohm resistance, B being positive. Find the current in each branch of the circuit. The diagram is not given. Yeah, see this question properly. The diagram only is not given, guys. So you need to be extremely, extremely careful. So there are basically A, B, B, C, C, D, D, A resistors. They are connected in series. Between A and C is a 1 volt cell. Between A and C is basically there is a cell. And similarly, between B and D is a 2 volt cell. They are connected in series, one after the other. Let's do this. A to B, B to C. Okay. C, oh, we should draw it like a square then, I believe. So this is B, then this is B to C, then this is C to D, and then this is D to A. This is 1 ohm, this is 1 ohm, this is 2 ohms, 2 ohms, this is also 2 ohms. Everyone? Okay, great. Now, what is also given? Between A and C, you have connected a battery where A being positive, oh, like this, okay, of some internal resistance like this. And what is the voltage? 1 volt, 2 ohm. 1 volt, 2 ohm. Between B and D is 2 volt, 1 ohm, where B is positive, okay. Yes, this is 2 volt and this is 1 ohm. Oh, so this is the circuit. The main thing is first figuring out how the circuit is going to look like. Without that, you cannot solve the question. Is this absolutely clear? Very good. Now, let's redraw it properly. I mean, let's open this up. Let's make it look very nice. So I think I have drawn one diagram, something which looks very nice. It's the same thing. I just opened it up, guys. I have made this side AD and DC flat so that this battery is below. So ADC will be flat. Check it out. Yes, ADC is flat. BD is over here. Between A and C is this battery and 1 ohm here each. So 1 ohm and 1 ohm here each. So when you open this up, this will go over here. This line I have made it vertical. That line I have made it vertical. Just making it look good. Is this okay, everyone? Is this Wheatstone? Is the question. Is this really a Wheatstone? Is the question. Yes, come on, think and tell me. Is this really a Wheatstone? Yes or no? Come on, everyone, everybody, let me know quickly in the chat box. This is going to be interesting. This is going to be interesting. Lot of people are going to think, sir, 1:1, 1:1, 1:1, 1 by 1, 2 by 2. Yeah, sir, Wheatstone. So, in that case, this guy and this guy, the voltage should be same. No current should go. But then what is this battery doing? What is this battery doing? It is creating a voltage difference. So these 2 points can't be at the same voltage then. Because there is a battery, it is not a galvanometer. Only when there is a galvanometer, resistor, capacitor, inductor, or a wire, then only you can eliminate it. Not when there is a battery. Not when there is a battery. Yeah. So what happens now is that you have no other option but to start assuming some currents and all of that. So let me just get rid of these stupid currents as they have marked. I will assume my own currents. So there is no other way to solve this particular problem, guys. Yeah. So you have to start assuming some currents because there is no other way apart from using Kirchhoff's laws. Is that okay? There is no other way. Okay. So start assuming currents. Keep in mind Kirchhoff's current law also and also Kirchhoff's voltage law. But Kirchhoff's voltage law will come later on. That's okay. So let's say through this battery, I take current I1. This current will get split into two. So let's say some current will split over here. Let's say I call it I2. If I1 gets split into I2, what will be the remaining current? Use Kirchhoff's current law over here. The remaining current will be I1 minus I2. Is that right? I1 minus I2. So this I2 will again come over here. It will split here as well as here. So let's say here it is I3 current. I3 current. So at this junction, how much current will go over here? Out of I2, I3 went here. So it will be I2 minus I3 current is going to go here. The same current will go over here also. I2 minus I3 until it meets over here again. These two will gather meet over here. I1 minus I2, I2 minus I3. Think what will be the current over here? Quickly, guys, what will be the current over here? Yes, at this particular 2 ohm resistor. I want the answer in the chat box. Very good, Gundumali, but don't have to spam. Sir, tomorrow very tough. Why, sir? See, if I tell you it is easy, then you will be chill. If I tell you very tough, you will study. That is why. Number two, suddenly CBSE will be like, this is the first paper, meaning first major paper. So you got enough time to study. They might make a difficult paper. Correct? Number three, JEE set a very good paper this time. So what guarantee CBSE won't? Number four, there have been instances where suddenly physics paper was moderate, above moderate in the past last 2 years. So why take a chance? These are the 4 5 factors why I told you the paper may be tough. I'm not saying will be tough. Yeah, come on. Yeah. So I2 will cancel. I1 minus I3. Very good. I1 minus I3. Very nice. I1 minus I3. They will merge and again make I1. Oh, at this junction. So this is our current configuration. This is our current configuration. Everyone with me? Very good. 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 Now you just have to apply Kirchhoff's voltage laws. Just have to apply Kirchhoff's voltage laws. You decide the loop and accordingly you can apply. Because there are three variables, we need three loops. So choose some loops, guys. It's not that difficult. This loop first, maybe. Then, oops, I don't want the answer. Then if you choose this loop, then what will be the equation looking like? Let's say we start from here. Always show the starting point. First, I'm going across the battery, increase of plus 2 volt. Okay, minus across the resistance in the direction of the current, it will be decreasing voltage. So I into R, resistance is 1 ohm. Here again across this resistance minus I2 into 1. Across this resistance minus I3 into 2 is equal to 0. So therefore 2 minus I1 minus I2 minus 2I3 is equal to 0. This is your first equation. Similarly, we can take this equation also. What is the harm? Correct? We can take that equation, or if you don't want, we can take even this equation also. No harm in that as well. Okay, so if you want, we can take this particular equation, loop, to make a Kirchhoff's voltage law equation. So let's say we start from here. We are going here from negative to positive terminal, so plus 1 volt. Then I'm going across this resistor, but current is going in the opposite way. So when I travel opposite to the current, it is plus IR. Current is I2 minus I3. Resistance is 2 ohm. Then I go across this resistance in the direction of the current, it will always be minus. So minus I3 multiplied by 2. Here I am going opposite to the direction of the current. So it will be obviously plus I1 minus I3 into 2. That again I am back to original position. So that is equal to 0. So you can write 1 1 plus 2I2 minus 2I3 minus 2I3 plus I1, sorry, 2I1 minus 2I3 is equal to 0. So if you want 1 plus I2 is there only once and I1 is there only once. So plus 2I1 plus 2I2, I3, 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 3 times. So 3 into 2 is 6 minus 6I3 is equal to 0. This is equation labeled 2. Is that okay? This is your second equation. Just check this out. Everyone? Yep. How many of you got this? How many of you got this? Just check. If you are using this particular loop, yeah, starting from this point, in the direction of the current, the voltage will drop across the resistor opposite to the direction of the current plus IR for the resistor. Okay, straightforward. One last loop. See, we took that one, we took this one. I think one resistor is left out. We need to take that also. Yes, we need to take that also. So why not start from here, go here and come back over here. And let me start from here. So first is a battery. So plus 2. In the direction of the current across the resistance, a drop of I1 into resistance, which is 1. Here also there will be a drop minus I1 minus I2 into resistance, which is 1. Here also there is a drop minus I1 minus I3 into the resistance, which is 2. That will be equal to 0. Just check this out. So 2 minus I1 plus I2 minus I1 plus, sorry, this is into 2. So minus 2I1 plus 2 times of I3 is equal to 0. So this will be 2 minus is 2 times of I1. Oh, sorry, I1 is again there here also. So minus 2 times minus. So minus 4 times of I1 plus I2 plus 2 times of I3 is equal to, is that right? Yeah, correct. Is equal to 0. This is equation labeled 3. So you have first equation, second equation and the third equation. Solve these three equations, my dear students, you will get the answer. Yeah, solve these three equations, you will definitely get to the answer. Yeah. So once you do that, so just say solving equation number 1, 2 and 3. You will get the value of I1, you will get the value of I2, you will also get the value of I3. So these kind of questions, please practice 1 or 2. Only then you will be confident about applying Kirchhoff's laws. Deepak already is telling some value, 0.8, 0.6, 0.3. 0.8, 0.6, 0.3. Just check it out, guys. What Deepak is saying, if it is correct. 0.8, 0.6, 0.3. 0.8, 0.6, 1.4. Yeah, it is satisfying equation 1. So I'm guessing it is correct. Yeah. Yeah, minor mistake will make a big problem. So just see if you are getting, after solving, 0.8, 0.6, 0.3 amperes. Okay? Great. Awesome. Now I have kept, I think, one more question like this for a Wheatstone's bridge as homework. Similar question, but unbalanced Wheatstone. Yeah, it's an unbalanced Wheatstone. You will see this after you try to solve it. It will be an unbalanced Wheatstone, so try to do it. Yeah, this is your homework. Answer is kept on the next slide. Now let's revise the graphs, my dear students. Shall we start with the graphs? Everybody show some fire in the chat box. Should we consider the internal resistance? Of course, that is what we have done everywhere. If you notice, like for example over here, what did we do? 2 volts minus I1 R1. What is that R1? 1 ohm. So this is your internal resistance. So you have to consider it. You have to consider it. Okay, great. Let's revise some graphs. Let me also open up my NCRT soft copy so that I also remember if I've missed any graphs or in case anything which has to be revised. Starting from electrostatics, guys. Yeah, I'll be starting off from electrostatics. Hmm. 1 second, let me just open it up. My NCRT. Okay, fine. Shall we begin? All right, shall we begin? Okay, so let's revise the graphs quickly. All these graphs, whatever I'm going to give you, please, please, please remember all of them. Okay, so first things first, for Coulomb force, for your Coulomb force, and field, due Coulomb force and field. So formula for force is K Q1 Q2 divided by R square, and the field formula is K Q by R square due to a point charge. The graph looks something like this. This is your distance, this is your force, this is origin. Similarly, over here, this is distance, this is your field, this is your origin. Here, because it is inversely proportional to r square, it will look like this, a curve 1 by r square. Same thing is also valid for field also. So again, it will be like this, inversely proportional to r square. So both of them are just some curves, but they are not parabolas or hyperbolas or anything like that. Okay, so don't get confused between them. Very good. Awesome. And in case you have forgotten to smash the like button, please do that because I'm going to give you the handwritten notes. I want 1K likes before the session ends. Then I will give you the notes today itself. If you don't make it, then I will give it to you tomorrow after the exam. Come on, smash that like button right now. Yeah, very good. Awesome. Next important graph is for potential energy, potential and potential energy. Potential energy is K Q1 Q2 divided by R, and potential is basically KQ divided by R. So again, over here, both the graphs, you will see will look like this only. This is also inversely proportional to R, inversely proportional to R. They are rectangular hyperbolas. Rectangular hyperbola when it is 1 by r proportional. There is also one more interesting graph where on the same chart, they compare both field as well as potential. So if potential is like this, which is inversely proportional to r, and this is potential graph, field is 1 by r square, that field graph looks somewhat like this. Yeah, so this is the field graph and this is inversely proportional to 1 by r square. Yes, the field comes below the potential after large distance, because when the distance is large, the field will fall faster. R square, right? So for large distance, the field will be much lesser than the value of the potential. So this is another interesting comparison graph, which is something given to you. Okay. Is this clear? Everybody with me? Awesome. Yeah. Great, great, great. Then you have electric field lines and equipotential lines for different uh, things. Like if you start for a positive charge versus a negative charge, how will the field versus the potential lines look like? So these are isolated charges like this, then like this. The fields will come radially outwards. You should know this. Here, for a negative charge, the field will come towards it radially inwards. These are the electric field lines. Electric field lines. At the same time, equipotential surfaces and equipotential lines, they will look like this. The next line, I'm drawing it at much larger distance like this, and same thing over here. Like this. Here, you will notice this is V1, this is V2, this is V3. V1 will be more than V2 will be more than V3. Here it is exactly opposite, V1, V2, V3. Field always goes from higher to lower potential. So V3 will be more than V2, which will be more than V1. That's how the equipotential surfaces will look like. Then, then you should also know it for multiple charges like dipoles, or basically two equal charges or two opposite charges. Yep, together. So that was also something which is very important. Either both are positive or both are negative, one and the same thing. You will see very similar field lines. So it will look something like this. The field lines will never intersect. They will try to bend when they are trying to come close. So that is how the field lines will look like, guys. That is how the field lines will look like. Yeah. So this is how it will look like. These are the electric field lines due to like charges. So field due to like charges. Due to like charges. For negative, the only difference is the arrow marks direction. It will be towards the charge because field will terminate on a negative charge. That's the only difference. Is that right? Okay. Similarly, if you take a dipole, one is positive, of course, one is negative, then how will the electric field lines look like? They will start from positive and they have to go towards the negative charge. So they will look something like this, like this. Yeah, you can see that. This is how the electric field lines will look like. Not showing the other lines. They will keep on coming like this from bigger, uh, faraway regions. Okay, so this is field due to a dipole. Field due to a dipole. Again, something which you should definitely remember, which is there in your NCERT. Is that okay, everyone? Clear? Awesome, awesome. Now, just like we have drawn equipotential surfaces here, you should be also able to draw on the same thing. How will the equipotential lines look like? How will the equipotential lines look like for a dipole and for like charges? So always field lines are perpendicular to potential surfaces. Remember that, and field goes from high voltage to lower voltage. Just keep that in mind, okay? So here it will look something like this. Yeah. And then what happens is it will merge, and that's it. Here it will merge again. This is how the equipotential lines will look like for like charges. Similarly, if you draw it for a dipole, this equatorial plane will be one of those lines. Equatorial plane will be one of those equipotential lines. The rest of the lines will look something like this. So these are the equipotential lines. Again, equipotential lines for a dipole. Is that okay? Always show it perpendicular everywhere. Automatically, if you know the field, you can draw the potential. If you know the potential, you can draw the field. Is that understood, my dear students? Very nice. Then the next one which you should know, the next one you should know is for a sheet. For a sheet. This is a sheet of charge. This is a sheet of charge. This is a sheet of charge. Charge sheet. So the equipotential surfaces will be just parallel to this. That's all. So just show things like this and you are sorted. These are your equipotential surfaces, and then when you talk about field lines, they will just go like this. They will be just parallel lines. Like this. So these are your electric field lines. Electric field lines, always from higher voltage to lower voltage. So this is equipotential 1, equipotential 2. V1 will be more than V2 because field is going from higher to lower. And this field is basically a uniform field. This is not non-uniform because the field lines are parallel to each other. So therefore, it is a uniform field. Is that okay, everyone? Yep. Great, great, great. Dark Wolf, the live will start tomorrow at 5 o'clock. Yeah, that live will start tomorrow at 5 o'clock. All right, all right. Great. Then the next diagram, let me open up NCRT, guys, again. The next diagram which you should know. Yeah. The Ohm's law, how will it look for ohmic versus non-ohmic devices? Yeah, this is another important thing. Yeah. This is another important thing which you should know. You might have seen this diagram. One second, let me open up the. Hmm. Hmm. Yeah. So this particular diagram, guys, where you have voltage and current, that's it. So current is there, voltage is there, or you know, uh, here also you can plot voltage. This is particularly current. Okay. And similarly over here, voltage and then current. Okay. Always plot voltage on the x-axis. Sorry. Always plot voltage on the x-axis. Yeah. And then for a conductor, the graph will be like this. For a conductor, the graph will be like this, where the current will be directly proportional to the voltage for a conductor. For a conductor. Then for a PN junction diode, for a PN junction diode, the graph will be like this. This is for a PN junction diode. And for a compound called GAAS, yes, for a compound called GAAS, it will look something like this. It goes like that and then goes like this and like this. This is for GAAS compound. Now, out of this one is ohmic device. Ohmic device because current is proportional to the voltage. Here it is not proportional. So these both are non-ohmic devices. Non-ohmic devices. So to show that these graphs are given to you. Is that okay, everyone? Yeah. Yes. Ga for gallium, As for arsenic, gallium arsenic compound. You should know that graph. It looks something like this. Increases, decreases. That is just to show non-linearity or voltage and current not being proportional or resistance not being constant throughout the region. Then there is a graph of variation of resistances with respect to temperature. Yes, the variation of how resistance changes, resistivity changes with respect to temperature. So like this, and like this. So everywhere you have resistivity, this is temperature, resistivity versus temperature, resistivity versus temperature. First we start for how does it look for a conductor? How does it look for a normal conductor? For a normal conductor, when you increase the temperature, the resistivity will increase. What should happen? The resistivity should basically increase. So you should see a straight line. So, but the problem is after some time, it might not exactly be straight. It will start curving. So usually that graph slowly starts curving like this. But for a small region, over here, it is a straight line. So for small change, it is linear. But for a large change, it is majorly non-linear. But special conductors like nichrome wire, okay, in a decently large temperature, you will see it is almost like a straight line. Yes, for almost a very good range of temperatures, it is a straight line. It is going to be a linear relationship for a good amount of range of temperatures. This is what it is for nichrome conductors. Okay. Last thing, for semiconductors, or basically, say for example, gallium arsenic devices, the resistivity falls with temperature non-linearly. So the graph is like this. So when you increase the temperature, resistivity decreases. Yeah. Is this clear, everyone? Awesome. Awesome. We are cooked for real, Emperor. Depends. If you want to be the food, you can be the food, and then you can cook yourself. But otherwise, we can cook. We can cook CBSE tomorrow if you study properly. If you do all the graphs properly, then you will cook the paper. Yeah. So I feel you should not be the chicken. You should not be the one who is getting cooked. You should be the one who is the lion, who is the hunter, who is going to cook. Yeah. So let's fight for it, guys. You are the hunter. You are the predator. You are the wolf. You are the lion. Okay. So you are going to cook your meal tomorrow. Is that right, everyone? Okay. Perfect. 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 So that was one of the graphs which is there. Then which other graph is there? Huh. This particular graph. Yes, this particular graph. I've already discussed it, but still I will show it over here. This is terminal voltage. This is terminal voltage, and this is current. This is current. And this particular graph looks like this, where your E minus IR is equal to the voltage. So at any point, if you measure the voltage, this is the current. So it will be this. As you can see, this E is nothing but your Y intercept. So this particular value will be basically E. And your slope, the slope is basically negative R. So it is definitely negative. You can see that it is going down. All right. And this particular point, when you notice that the voltage is E, that means the current is 0 at this particular point. Current is 0 and the voltage value is E. This happens when when it is an open circuit. When it is basically an open circuit. Whereas this one over here, where the current is maximum as well, but the voltage across the terminals is zero. This current is basically the maximum current. This will happen when the circuit is basically closed. You short the terminals of the battery. You short the terminals of the battery, meaning something like this. So this battery is there, this internal resistance is there. You just connect it like that. Whereas in this particular case, you have just measured the voltage by using a ideal voltmeter. That's all. It's an open circuit. The open circuit voltage is always the EMF that is also there. And the closed circuit, when you short the terminals, then you get maximum current, maximum current will flow. Immediately the battery will get discharged. Yeah. Is that okay? Great, 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 great. All right, very good MC edits. I'm so glad. Ooh, Emperor says you don't cook in this subject, you get cooked by it. Very true. It depends on how are you the predator or are you the prey. Yeah, so depends on so many things. All right, let's go to the next thing. I think we have magnetic coils, if I'm not wrong, magnetic coils, solenoid and all of that, the graphs and everything. Mm, hmm. Okay, so the next important thing, if you have a coil carrying current, this is a coil carrying current, then how do the magnetic field lines look like? That's the first thing. So the magnetic field line will be like this from here, like this from here, and these field lines will go like this, like this, like this, like this. They will go like this. They will come from here, go like this. Oops, like this. Of course, this will be also there. Okay, something like this. So this is how the magnetic field lines will look like. Now, there is also a graph of how the field strength varies on the axis, how the magnetic field which is there on the axis will change, which has a formula mu naught I r square by 2 r square plus x square whole raised to 3 by 2. This is on the axis. This is, remember, the axis of the coil. How does that particular magnetic field change? Anybody remembers? Say if x is 0, you get maximum field. If x is very large, you get minimum field. In fact, it tends to 0. So it goes basically like this, and here also it goes like this. So basically it is nothing but it increases, becomes maximum, and then tends to 0. So it is maximum at the center. So it is maximum at the center of the coil, at the center of that particular coil. And very far, very far, the magnetic field tends to 0 because you are very far. So the effect will be very less. Is that clear, everyone? Awesome, 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 awesome. Great. You should know all these things. You should know all these things, my dear students. These are all just the graphs which we are doing. Mm, One second, I closed my tab. Okay, then the next one which you should know is you have a cylindrical conducting wire whose radius is r, and the current is flowing throughout that particular cross section. This is how the current flows, and there will be magnetic fields inside as well as outside. So when you are inside, the magnetic field lines will be like this. So this is how the magnetic field will be when you are inside, and when you are outside, something like this. Okay, so when you are inside that wire, the magnetic field is mu naught I into small r divided by 2 pi capital R square. R is the distance from the center. But the same thing when you go outside, when you are outside that particular thing, it is just mu naught I divided by 2 pi small r. Now this graph has again come many times. It's also important from many competitive exams point of view. So here you have your magnetic field. You have your magnetic field. You have distance from the axis or from the center of that wire. So initially what happens is the field is linearly proportional to r. The field is linearly proportional to r. So the graph goes up like that. So you will see it is directly proportional to r, but it is then inversely proportional to r over here. So it is inversely proportional to r over here. This is a hyperbola. This is a hyperbola, not any ordinary hyperbola, but a rectangular hyperbola, because it is inversely proportional to r. And at the same time, as you can see, exactly at distance being r, which is on the surface, the magnetic field is going to be maximum, exactly on the surface. Is that okay? All these things you should definitely know. Yes, very good. Awesomeness. Great, great. Yeah. If you want to make it look much better, you can just show it as dotted lines because they will technically be hidden, the ones which are outside. Okay. Next, let's go to the next thing. How will the graph of susceptibility look like? Susceptibility look like for different types of materials. Susceptibility versus temperature, magnetic susceptibility versus temperature. First one, diamagnetic, diamagnetic. Second one, paramagnetic, paramagnetic. And the third one is basically ferromagnetic in nature. When it is a diamagnetic substance, it is direct, it is going to be a constant. Basically, it is independent of the temperature. It is independent. It does not depend on the temperature. So susceptibility is just going to be a constant. When it is a paramagnetic, it is just inversely proportional. Susceptibility is inversely proportional to temperature. And that constant is called C. This law is called as Curie's law. Curie's law. When it is a ferromagnetic, till a certain temperature, the susceptibility is very, 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 very high, too high to be even noticed. Immediately after this critical temperature, it becomes like this. That means it becomes paramagnetic in nature. Before this, it was ferromagnetic in nature. This particular temperature, after which ferro becomes para, this is called critical temperature. Critical temperature, or basically your Curie's temperature. This is Curie's temperature. This is called Curie's temperature. Is that okay, my dear students? Everybody? Yeah, earlier it is ferromagnetic. After that critical Curie's temperature, it then becomes a paramagnetic substance. Awesome. And if you want the law for it, the law goes like that. Once it is para, the susceptibility is 1 by T minus critical temperature. So you have to measure the temperature minus Tc. It's like shift of origin. So inversely proportional to T minus Tc. So that is the law for it. Is that okay, everyone? Shall we go ahead? Okay, awesome, 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 awesome. Okay, let's go to the next graphs which are there. Okay, hardly a few more minutes. We are almost done. It's not much which is remaining. In optics, there is only one major graph which you should know, and that is for prisms. Nothing else is important. Here you have incident angle, and here you have angle of deviation, angle of deviation, angle of deviation, my dear students. So it goes like this. Yep. And this one here, particularly, this happens when angle of incident is angle of emergence. This is your minimum deviation, and mu is equal to sine of a plus minimum deviation by 2 divided by sine of a by 2. And when that happens, this is equal, R1 is equal to R2. Yeah, all these things happen at minimum deviation. So this is another important graph in optics which you should remember. And there is no other graph which you need to know. Yeah, yeah, correct. Very good. Now, next, let's go to, let's go to AC circuits. Yeah, I think Yugant was telling, sir, what about LCR? Yes, we are coming to that also. Yep, we are coming to LCR. Okay, 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 okay. So for LCR circuits, uh, this is time, time, time. First is when you have a resistor connected to an AC circuit, then you will have an inductor connected to an AC circuit. Lastly, you will have a capacitor connected to the AC circuit. All right. So these three things are there. Okay. Ray diagrams of optical instrument. Yeah, those are diagrams. If you want, I'll show it to you. No issues. I'll come to that. Ray diagrams of optical instruments if you want me to show. Hold on, just give me 1 second. So here, always show the current graphs first. That is easier. Current is first. So this is basically your current, current, and the phasor of the current can be easily shown like this. The current phasor like this. So this is your current phasor, current phasor, current phasor. Now comes the voltage phasor. For resistor, it is the same. Current is V by R, V is equal to I into R. So it will be just like this. So this is basically your voltage, and the voltage will be in phase. The voltage will be in phase. The voltage will be in phase, so there is no phase difference at all. Whereas for inductor, remember, the voltage is ahead. The voltage is ahead of the inductor by 90 degrees. So already it would have reached some maximum value. So therefore it will start like this. It will go like this. Start like this. It will go like this. So there is a phase difference between them. And in case of capacitor, the voltage is behind the current. It lags it. It is behind the current by 90 degrees. So it will do whatever it is doing later on. So it will be somewhat like this. So you can see it is coming up after some time. So it is behind. So this is voltage. Okay. So these three graphs are in AC circuits. Apart from that, you should also know the resonance curve of LCR circuits. Here you have your omega of your AC source, angular frequency of the AC source. Here you have the current in your LCR circuit. And how does that particular graph look like? This graph looks like this. Yep, everybody, the graph looks somewhat like this. Everybody remembers this? And yes, it is maximum. It is maximum over here when this omega is the natural frequency, which is 1 by root of inductance into capacitance. This is the maximum current which can go, which will be the total voltage divided by the resistance. When this happens, it is called as resonance. And at resonance, inductive reactance is equal to capacitive reactance. Therefore, the total impedance, which is root of R square plus XL minus XC whole square, will become just XL and XC are equal. It will just become R. You will also see phase difference is 0. So cos phi will be 1, which is also the power factor. And this also means maximum power will be delivered in the circuit. Maximum power will be delivered in the circuit. All these things hold true. You should know that. Okay, clear? Very good. Yep, awesome. Yeah. So in case you wanted to know for here who needs whom, so I will say voltage leads. Voltage is leading by 90 degree. Here voltage lags by the current by 90 degrees or pi by 2. Here it is voltage is in phase. There is no phase difference in case of pure resistor. All these things you should definitely know. Talking about the ray diagrams for your optical instruments, I'll just give you a heads up. Do not draw the ray diagram first. Always show the object and the image first and then show the ray diagram. That will be much easier. Yeah, a lot of people show the ray diagram, then try to locate the image. I suggest don't do that. Do the exact opposite. Yeah. So if you are talking about a simple microscope first, oops. This is simple microscope for a simple microscope. So this is how it looks like. The object will be here. The image will be here. This is the object. This is the image. Your eye, human eye, will be somewhere over here. Okay. And the ray diagram. This is very, very important. The ray diagram. How will it look like? Observe carefully. One ray which is going here will bend, but such that it should bend like this. Show it going like that, exactly through this point. So drawing the images first helps us, but obviously this particular ray is not the actual ray. It is just an imaginary ray because I have extended it behind. You need one more ray to do this, and that can come from over here like this. It is passing through the optical center, which will go undeviated. Again, this is just imaginary. You have extended it behind. So now show the arrow marks. That will be easy. This will be like this. This will be like this. This will go like that. This will go like that. This point will be obviously the focal point over here. Yeah, this point will be the focal point. Everybody with me? Very good. And the secondary focus will be over here. This is F2. Secondary focus. So the object is behind the or before the focus and the pole. That's how it is. Yeah. Great. Great. So this is that ray diagram which you will be showing. This image is obviously a virtual image. Virtual image. It is also erect and it is also magnified. This is also magnified in nature. You should know this. Then comes your compound microscope. Compound microscope. Compound microscope. Let's draw this. Compound microscope, guys. Start with your principal axis, of course, again. Start with your principal axis. Just here. Okay. Two lenses, objective and eyepiece. Eyepiece will be bigger in this case. Eyepiece will be bigger. Objective lens is smaller. Keep that in mind. Okay. Then your final image may be formed here. Chumma I'm showing. And your intermediate image could be somewhere, let's say here. And then your original object might be here, somewhere like this. So these are the things that you will show. Now comes the ray diagrams, how you are going to draw it. The ray which is parallel to the principal axis after refraction will pass through the focal point. Oh, sorry, like that, my bad, like this. And another ray, I can just show it. Okay, it's not that great. Anyways, so actually I should have shown it somewhere over here, maybe, then it would be better. I'm back tracing it from where it is coming. So our object is here. So this is our object. This is our objective lens. Objective lens. This is your eyepiece. This is your eyepiece. That means your human eye will be somewhere over here, like this. Okay, this is your intermediate image. It is not your final image, which will now be the object over there. And then the final rays will come over here like this. It will bend, and when it bends, it will go like this. And another ray, show it. Okay, it is not that great. So let me do one thing. I'll just draw lines like this so that I can deliberately make them meet somewhere, nothing more, and then show it like this. Chumma, I'm deliberately showing it meeting over here. So I will then directly take it somewhere here. Okay, that's it. So then you can basically say this is extended lines. These are not real rays. Yeah, these are not real rays. So I'll just show it as dotted lines. That's enough. So our job is done. Now the arrow marks will come over here, here, or they will meet over here like this, and over here they will go like this, undeviated. Parallel will then pass through the focal length of the eyepiece. This will be the focal length of the objective. That's it. Is that okay? So this is how the ray diagram will be. This is the final image that final image is virtual. It is also inverted, and it is highly magnified. So this is also highly magnified. So you can keep in mind all these things. That's how you can do this. Awesome. Okay. And of course, do not forget to show this as the length of the tube, length of that particular tube, which will be from here to here. Just show that. And also mark this as intermediate image. Intermediate image. So always, try to make the ray diagrams which will fit in the paper, or else when you try to draw those ray diagrams, they will make the image somewhere out of the paper. So try to adjust first. You draw the rays, then automatically adjust the image, because you should know where the images come, how they look like. Okay. Yeah, this is like a skibidi microscope. Very true. Very, very skibidi microscope. Agree. Last one is your telescope. Is your telescope, guys. Yeah, this is your telescope. Again, over here, okay, start with your principal axis. Start with your principal axis. Objective will be very big. Eyepiece will be very small. Okay. And the object will be very, very far away. So the rays will come from infinity, and they will basically make the image over here. So the object is very far away, and this is your objective lens. Objective lens. The first intermediate image is formed over here. This is where your intermediate image is going to be formed, which is inverted, real, and everything. And it is roughly formed close to the focal length, very close to the focal length of the objective. Then what you do is make these rays go like this, and like this. Then they will go like that, and then you extend them backwards so that they intersect somewhere. So I'm showing them to be intersecting over here because I have to make them intersect somewhere. So then what you get is your final image over here. This is your final image. Again, it will be very far. It will be virtual. It will be inverted. Not just that, it will be also magnified. It will also be magnified in nature. So all these things you should show. That's it. And yes, for the eyepiece lens, this particular focal length, you keep it like this. So focal length of the eyepiece will be somewhere here. The intermediate image is slightly before the focal point. That's how it is. Yeah, cool. Yeah, awesome, awesome, awesome. Great, great, great. Is this clear, my dear students? Can we go ahead? Yeah, very nice, very nice, very nice. Then, one very important graph in optics, wave optics, sorry, that you get. Sorry, not like this. This is intensity, this is distance. This is intensity, this is distance. This is your center on the screen. This point is your center on that particular screen. This diagram, what I'm talking about, is Young's double slit experiment. This is single slit experiment. basically we are talking about diffraction versus your double slit interference. Double slit interference. So how do the intensities look like? For a Young's double slit experiment, well, the graph looks something like this. All the maximas are of the same intensity. All the minimas are also of the same intensity. Slightly weird to draw it, but I will try my best. All the maximas are of the same intensity, like you can see, and they are equally spaced, but that is not what happens. That is not what happens for interference, for diffraction, my bad. The first intensity, first maxima is very large, then it is smaller, and then it is even smaller. And even the gap between the maximas is not even. The fringe width is not really even. So it gradually reduces. As you can see, it is reducing. The maximas are not of the same intensity. Even the gaps are not the same. Yeah. So this is one major difference between diffraction pattern and interference pattern, which you should be aware of. Okay. Fine. Then next graph, let me check what else is there. Next. Phasor diagrams, Mohan, we have already done. AC circuit, we just did it. I don't know whether you were there that time. Yeah, we have just done it. See, right over here. Phasor diagrams have just shown it for everything. Okay. Now, next, for photoelectric effect, what are the different graphs? All the important graphs for photoelectric effect, guys. Photoelectric effect. Let's see. Oops. Let's see what are the different graphs. So what are these graphs? Let me show you. This is voltage. This is current. Same thing here. This is also current. This is voltage. For the same light, for the basically, yes, for the same light and for different lights, you will see different graphs will be there. Yeah. For the same color of light, you will see the graph will look something like this. This is I2, this is I1. Intensity is more. Same light. This is same lambda, same color. This is your stopping potential. Stopping potential. Stopping potential is independent of intensity graph. And the second important graph is this one. Oops. Take this slightly over here. You draw the graph for one material with a particular intensity. You draw it for another color, same intensity. It will have different stopping potential. This will be minus V2. This will be minus V1. So different colors, different lambda, but same intensity. The current, maximum current will be also same, but they will have different stopping potential. This is another important graph which you should know. There are a lot of case study based questions also which can come over here. Then you have the graph of how intensity of the light, from this only you can see how intensity of the light affects the photocurrent, and that graph is fairly easy. It is just a straight line. The current is directly proportional to the intensity. It's a linear relationship, and it obviously passes through the origin, because if there is no light, no intensity, current is also going to be zero. Yes, it starts from zero only. The last graph over here, yep, now this is also important, guys. The last graph over here. Any guesses? There is one more graph where the graphs are straight line. Yes, the graphs are basically straight line. One is stopping potential on the y-axis versus your frequency, This is drawn for different metals, It is like this. Maybe from another metal, it will be like this, But if you extend it behind, what does it exactly give you? So first of all, this graph is a straight line, and this point over here is the threshold frequency of this color, FO of the first metal. This is basically the threshold frequency of the second metal. So these are basically different metallic surface, different metals which have the same slope. Yes, the slope is the same, and slope is h by e. That is always going to be the same. The slope will be the same. Keep this in mind. Yep. Okay. But the y-intercept will be different. The y-intercept will be different, like this much amount magnitude wise will be the work function divided by E. Yeah, work function divided by E is what this will be, but this will be for the first metal. For the second metal, it will be entirely this much, which will be phi 2 divided by E. So that's the y-intercept. It will depend on the work function of that particular metal. Is this okay, everyone? All right, all right. So tomorrow morning revision session 1 hour to 1.5 hours, not more than that. All right. Then what other graph is remaining? Let's have a look. Let me see. In atoms, this graph is there where you have the number of atoms versus the scattering angle which you should know. Yes, the number of atoms which are talked about versus the scattering angle. This graph you should definitely know. It is something basically like this, and this goes on till 180 degree. This goes on till 180 degrees, and it starts from 0 degree. For 0 degree, most of the atoms are unscattered. Very few atoms are these are not number of atoms, these are number of alpha particles, my bad. Number of alpha particles, my bad. Number of alpha particles which are scattered. So for 180 degrees, very few alpha particles are turning back by fully 180 degrees. Yes, you should know that. Correct. Very good. Very good. Awesomeness. Awesomeness. Then 1 second. There is one more diagram which you should know. I'll just take it from here. This particular diagram. Yes, this particular diagram you should definitely know. I will just copy it here so that when you take the notes, you have it. All the spectrums, the energy levels. This you should definitely know. Please revise this graph. If you remember the values, it will be much easier for you to visualize, calculate, and not waste a lot of time. Okay. Then next thing which you should know is this particular graph of distance of separation, distance of separation versus the energy, versus the energy between nuclear particles. This is for nuclear forces. Nuclear forces. Yes, nuclear forces. This particular graph is also there. Yep. Have you seen this? Nuclear forces, potential energy versus the distance. Yeah. So this particular graph also you should know it is like this and goes like that. Yeah, it goes like this and goes like that. Usually it is very low when it is close to a femtometer. A femtometer, then it is lowest or minimum. That means it is most stable, and then it has strong attraction which is there, strong attraction which is there. And within few like 5, 6 or 10, 15 Fermi meters, within a few Fermi meters, then it vanishes. Nuclear force is negligible, That is what this particular graph tells you. When you are very close, then it is repulsive in nature, because potential energy goes positive, then it is repulsive in nature because it is positive, it is going to become unstable. Potential energy is going to go higher, so it is not going to be so stable, so it goes into the repulsive mode. That's what happens. Very close. Is that okay? Yep, very good. Then the next curve that you should know in nucleus, the next curve which you should definitely know in the nucleus is this particular graph, where you have the binding energy per nucleon, which gives me the stability of nucleus, versus the atomic mass number. And this graph goes like this somewhat, and then it goes like this. Yes, it goes somewhat like this and then goes like that. It is maximum. Where is it maximum? This is very important. For iron, yep, this value is maximum. For iron, this binding energy per nucleon is maximum. So this is going to be maximum. Something around 8 point something mega electron volt per nucleon or something like that. Is that okay? How many of you remember this, guys? Remember? Yes, no? Paka? Very good. Awesome. Okay. Last few graphs in semiconductors coming through. Last few graphs, guys, in semiconductors. This is your current. This is the voltage that you apply. This is origin or zero current, zero voltage. This graph going like this and suddenly shooting up. Yep. This is which part of the graph? This is which part of the graph? It is basically your forward bias. This point happens to be your knee voltage. This is your forward bias. This side is forward bias, meaning our diode, which is PN junction diode, this will be connected to positive, this will be connected to negative. Also over here, it is non-linear, so voltage and resistance, they are not current, they are not proportional. So voltage is not proportional to the current. Keep this in mind. Although there is one particular thing which is calculated on this graph, and that is if you take a small change in the voltage and there is a small change in the current. So if I call this as delta I and this value as delta V, so you have some term called as dynamic resistance. Dynamic resistance. Just like resistance, V is equal to IR, so R is V by I. Here it is delta V by delta I. It is not normal resistance, it is called dynamic resistance. Yeah. Okay. Chat is shocking. What is shocking? Bruce, Shaswin, or yeah. What is happening in the chat? I don't know. I have not read the chats for 1-2 minutes. Need to mention other elements. Which other elements? Oh, Daniel, you want a session to end? Very simple. Just exit YouTube app. The session has ended for you. Simple. Yeah. And here in the reverse bias, it is like this, very, very, very small. This is called as your leakage current. Leakage current. This is reverse bias. Current will go like this. This is connected to positive. This is connected to negative. And then there is a avalanche breakdown. Avalanche breakdown. And this particular value, which is constant, is called as the breakdown voltage. Breakdown voltage. These are the things which you should again definitely know. Lastly, this is input. This is half wave. This is full wave. We are talking about rectifiers, which is basically going to convert AC into DC voltage. So if the input voltage, let's say, is like this, in case of half wave rectifier, only half of the wave comes out. That's it. The other half will not come out. In full wave rectifier, both the waves, both the halves will get rectified, meaning they will become unidirectional. It will not be in the negative half cycle, which says the voltage, if it is positive, will remain positive, which means the direction of the current or the voltage is always going to be the same. So this is the difference between half wave rectifier and full wave rectifier. You should know these you should also know these graphs as well. Yeah. Is this clear, everyone? Very good, very good, very good, very good, very good. Electromagnetic spectrum, please, yeah, remember that. Electromagnetic spectrum, you should definitely remember that. So this is very, very important. Electromagnetic spectrum. It starts with visible light, which is a very small portion of it. And in that small portion, you have violet, which is around 400 nanometers. And you have red over here. Sorry, you have red over here, which is around 700 nanometers. In between, somewhere you have yellow, and of course you have VIBGYOR, violet, indigo, blue, green, yellow, orange, and red. All those colors are there. So this is your visible spectrum. This is your visible light. If you mix all these colors together, you get white color light. Now, when you go slightly on this side, you get ultraviolet, UV. Okay, you get ultra, beyond violet, ultraviolet. It is not visible to you. Below this, you get basically infra, below, infrared, infrared. This is in 400 nanometers. You decrease the wavelength to few nanometers, like below 400 nanometers till 1 nanometer, and so on and so forth. After that, below 1 nanometer, in Armstrong, when you go, you get basically X-rays. Yes, you get X-rays. It typically goes in Armstrongs, few Armstrongs. After X-rays, what you get is gamma rays, which are again used for treating cancers, very energetic. They are in the range of femtometers, the wavelength. And then after that, you get cosmic rays, which have no end, cosmic rays, which are very, very energetic. On the other side, over here, after infrared, you get basically microwaves. So from 700 nanometers and beyond, so it will become 700 to 1000 nanometers, 1200 nanometers, around that range. It is infrared. Once it becomes 1000 nanometers, it will become micrometers. So that micrometer to millimeter range, millimeter to micrometer range, it is microwaves. And then before that, it is going to go to millimeters, and more, it is meters. So you have long radio, short radio and long radio. Here you will have short radio, which is typically in few meters, and then you have long, which is typically in kilometers and beyond. These are basically radio waves. So this is your electromagnetic spectrum, which you should definitely remember, guys. Is that okay, everyone? Awesome. Yeah, great. So yeah, that's about it. I'm guessing I've not missed much graphs. Most of the graphs important are done. Now, I want one thing. If you want me to share the PDF, yeah, I don't know whether you guys have smashed the like button yet or not. So please do that. If you don't do that, I will not share the PDF, guys. If you want the PDF immediately, yo, what is this? Come on, guys. I want everybody to smash that like button immediately to 1K. What is this? Who are those 170 more people, odd people? I want them to quickly smash that like button if you want the PDF to be shared. Else it will not be shared. Should we show other atoms? No, it is not required. I mean, it's fine. You don't have to show. See, the last atom on the other side will be uranium. The first atom will be hydrogen. That's enough. Hydrogen, helium, lithium. Okay. Iron is there. Then in the end, uranium, radium, etc. That's enough. You don't have to show other atoms. Is that okay, knowledge V? Yeah. Galvanometer is there. Yeah. Range, better to remember it approximately. Yeah. Yay, I'm in Shreyas sir's board. Very good. Yay. Awesome. If I start now, what is the ripple factor? That and all is not there. I mean, don't worry about it. Yeah. Basically, it is how much variation is there in that rectified voltage, okay, as compared to your average value of that, as compared to the average value of that DC. So once you convert AC to DC, there is still some pulses. It is like pulses are there. So how much, variations are there compared to the average value of the DC? That is what basically gives you that ripple factor. So that's just an concept, and also formula wise, you don't have it. Molu's law is there. Yeah, Molu's law is there, definitely. Optical instrument sums are also there, but if you want to solve them, see, there are only three formulas. See, the major problem happens in microscope. The microscope related sum, I have done it yesterday. Please see that. That is the most complex sum. Telescope is simple. Fe by Fo is the magnifying power, and length of the tube is Fe plus Fo. That is very straightforward. Even simple microscope, 1 plus D by F or D by F. That's it. Nothing else comes. Only the microscope is going to give you trouble, and that problem I have solved it. So please check that out. I have done it yesterday. Where have I done it? CYQ. In CYQ I have done it. Okay, so please check that out. Time constant and all that is not there. Don't worry. Infrared is called heating ray because, see, normal human bodies at normal room temperature 300 Kelvin, the lambda, which is maximum by Wien's displacement law, which you have studied in 11th standard, thermal radiation which happens, is around that 700, 800 nanometers, which comes in the infrared region. That is the reason why infrared rays are also called as heat rays, meaning if the room is completely dark, our body is still emitting radiation, thermal radiation in the infrared region. So if you have an infrared camera or infrared detector, you can detect the human body. So it is also used as, you know, thermal vision in the night, especially by the military, to see if there is some enemy. Malu's law is basically for polarization. When unpolarized means light waves are oscillating in all the different planes, they pass through a polarizer, then the direction in which the light wave oscillates is only in one plane, so the intensity will become half. If unpolarized is there, it will become polarized, the intensity will become half. But if the light is already polarized and then it passes through the polarizer, if the polarizing plane and the light oscillations are making some angle theta, then the final intensity is the original intensity multiplied by cos square of the angle. Cos square of the angle. That is Malu's law. Yeah. That's what it is. All right. Great. How to study electromagnetic waves? Just go to videos, and if you want to still study, I mean, you have it. See, guys, I don't know why you guys have not yet watched these lectures. Yeah, I mean, why am I doing this? If you don't want it, then I will delete this. I mean, 10 hours, 4 hours, 8.5 hours, 5 hours, 5.5 hours lectures are there for all of you in detail. NCERT has been taught. What more do you want? What more do you want? Cool? Okay. Awesome. I'll see you guys tomorrow morning. We'll just do a quick, not more than revision. I will also motivate you and also wish you, and obviously we'll do a very quick revision. Okay. Just so that everything is there. Formulas will quickly go through, the graphs will go through, or whatever is needed will go through. Okay. Any doubts you have, you can ask me in the morning. So it will be like a very personal session for all of you. This is only for you. If you don't wake up, I'll feel very bad. So I want everybody to wake up and smash that like button for tomorrow morning session, guys. Where is that morning session? It is right over here. Already 11 people are waiting over here. Great. So guys, don't wait now. Don't worry. Wake up at 4:30, 4:45. Just attend this session. Smash your attendance right now. And also for this session, make it 1K like easily, only then sharing the PDF. Okay, bye bye. Take care. Have a great time. All the very best. All the very best. Hasta la vista.